I don't particularly care for my graph here on page 1. You may have printed this, you may not have printed this, but let me see if I can produce a little bit better graph of this using GeoGebra. I'm going to go ahead and open that up. Let's say here. Oops. The function is this. F of x equals this expression, kind of a rough looking expression, 3x minus 6 in the numerator, and in the denominator, square root of the quantity 4x minus 4, and of course that radical expression could be simplified. You could factor out the 4 on the inside, bring it outside, and have a 2 on the outside if you wanted to, but I'll just leave it unsimplified. Square root of 4x minus 4 minus 2. Now, if we were to consider the domain of this function, there are a couple of different ways where a number can fail to be in its domain. First of all, we'd have to be able to evaluate the square root of 4x minus 4, and we'd have to get a real number as the answer when we do that. So if we are going to get a real number when we take the square root of 4x minus 4, what must be true of 4x minus 4? What kind of numbers have real square roots?
Positive.
Positive. And also 0, right? So 4x minus 4 would have to be greater than or equal to 0. So 4x would have to be greater than or equal to 4. And if we have an inequality and divide both sides by a positive number, like positive 4, we leave the inequality symbol pointing the way it was pointing, and x would have to be greater than or equal to 1. And we look at the graph, and we don't see any points on the graph to the left of x equals 1 down here. Cut off my x-axis, that was a mistake. X equals 1, so no points to the left of that. So evidently 1 itself is in the domain. If we evaluate the function at 1, 3 times 1 is 3, 3 minus 6 is negative 3. What happens downstairs? 4 times 1 is 4. 4 minus 4 is 0. The square root of 0 is 0. All right, 0 minus negative 2, it's looking like negative 2 in the denominator, negative 3 in the numerator, and that's 1.5. So we see the point 1, 1.5. Now, that's the leftmost point on the graph. So the domain, as far as we're concerned, includes numbers greater than or equal to 1, except for one more. There's one more number that's missing from the domain. It's a hole in the graph, basically.
Where the bottom part equals 0.
Where the bottom part equals 0. So not only do we want the square root of the expression to give us a real number, when we subtract 2 from that, we don't want to get 0. So what's the value of x that's going to make the denominator equal to 0? Is it 2? 4 times 2 is 8. 8 minus 4 is 4. The square root of 4 is 2. And 2 minus 2 is 0. So what do we say? X is greater than or equal to 1, but x better not be 2. So the domain would be 1 to 2, not including the 2, and put the union symbol, and then 2 to positive infinity. Well, this problem is not asking us for the domain. I think it's helpful to consider what the domain is, but this problem is not asking us for the domain. It's asking us for the limit of f of x as x approaches 2. It would have had to pick a not so nice value of 2, something that's not in the domain, but that's what it wants. The limit of f of x as x approaches 2. let's back up just for a moment to look at kind of an informal definition of limit, and then let's see if we can find this value. So, so back to the notes here. If the values of f of x can be made as close as we like to L by making x sufficiently close to a but not equal to a, then we write the limit of f of x as x approaches a equals L. This is supposed to be the easy to understand definition of a limit. What's your first impression? How do you feel about this? It's like, oh yeah, that's obvious. I mean, just saying it out loud makes it seem mysterious to me. But of course, you know, I failed my limits test in Calc 1, so what do I know? Here's maybe a picture to go with that. If we got our function, and we're interested, let's see, we're interested to see what's going on close to x equals a. Maybe not equal to a, but close to a. And the graph maybe is doing something like that. And I'm going to draw a little circle there to indicate that maybe the function's defined at a, maybe it's not defined at a. Maybe there's a solid dot there, maybe there's an open circle there, but it's an open question at this moment, so something like that. It looks like if x gets really close to a, then f of x is getting really close to L, the y coordinate of that point, that little hole in the graph that I drew there. So some would say that the limit of f of x as x approaches a equals L, and basically that means we can make the value of the function as close to L as we please by requiring that x be no farther away from a than absolutely necessary, some predetermined distance. So, goodness, this graph is kind of flat here, close to L that I've drawn. So if we wanted to ensure that we get no farther away from L than this, I think we don't have to be really close to A at all, because if you look and see what's going on here, as long as x is between there and, goodness, we could go maybe all the way over there. If we evaluate the function anywhere in here, it's going to land us in between those two horizontal lines. If we make the horizontal lines closer to each other, we might have to scoot closer to A to make this happen. But yeah, it really looks like if we make x close enough to A, then we can ensure that f of x is as close to L as it needs to be. Well, when I move the slider here, what it's going to enable me to do is consider what happens to the value of f of x as x gets close to 2. So we can see the values here. This is, let's use this because it's a bit easier there. So here x is about 3, and you can see that f of x is about 3.62. So as x gets really close to 2, f of x is getting really close to what? 3. Now, when x actually gets to 2, the point disappears, because the point 2, 3 is not on the graph. It's a hole in the graph because 2 is not in the domain. Function is not defined at 2. So if we ask what's the value of f of x when x equals 2, well, it's undefined. But what's f close to when x is close to 2? Well, from the other direction, 1.5 something, 1.6, 1.7, 1.8, 1.9. What is f of x close to when x is close to 2? Well, it kind of looks like it's close to 3. Again, it disappears there. But that's the idea. It's the idea of what's it close to, the limit, not what it's equal to. The function itself, if we wanted to get weird and define this function to be 5 at 2, we could do that and it would still be a function, but the limit would still be 3 because the function's getting close to 3 as x gets close to 2. That's what we're saying there.
Basically what it would be, or what you're guessing it would be if it wasn't double.
Yes, yes, and when we talk about continuity in an upcoming section, we'll want to see how can we define the function so we can fill in the hole in the graph. And the limit, the value of the limit, is the value that we would use for that. So again, I don't care for my graph because I didn't include the origin or the x-axis or the y-axis. That looks kind of rough there, but I think the GeoGebra graph works pretty well. Let's consider this function. Maybe make a conjecture about the value of the limit of sine x over x as x approaches 0. Well, what's the problem when x actually equals 0? Sine of 0 is 0, but if we put a 0 in the denominator, we're looking at an expression that looks like this. This is our actually second example of an indeterminate form. Had we looked at this one up here, while it's true that 2 makes the denominator 0, it also makes the numerator 0. I didn't point that out, but 3 times 2 is 6, and 6 minus 6 is 0. So that's another example of something of the form 0 over 0. Now we're not saying that's equal to a particular number. It's just kind of a form that we consider because both the numerator and denominator are approaching 0 as x approaches a particular value. But that's example number 1 of this particular indeterminate form. And here is example number 2 of that same indeterminate form. If we look at the graph, it would appear that x is getting close to the y-coordinate of that point, which is 1. If we look at a table and just choose some values of x really close to 0, like 0.1 and 0.01 and 0.001, the value of sine x divided by x is getting really close to 1. Let's see if GeoGebra sheds any light on this. Maybe it will. I'll probably have to change the viewing window a little bit. So there's sine x over x. And let me take this. I no longer need the hole in the graph right there. But if I could change that maybe to the point 0.01, that could be useful. Because that's going to be the new hole in the graph. I don't know that in advance. I know that because I've already worked this problem. It'd be nice if I get it to do automatically, but no. All right. So we look and we see what's going on here. The as x gets close to 0. Is it going to let me get close to 0? Maybe not. As x gets close to 0, what's happening to the y value? 0.96, 0.97, 0.98, 0.99. Close enough to 1 to round it, rounding to 2 decimal places. A little bit anticlimactic there. But there we go. The point vanishes when we get to x equals 0 because the function's undefined at 0. But as x gets really close to 0, the function's getting really close to 1. As close to 1 as we need it to be. So I'm gonna say that the value of the limit, say it like this, or let me just say it like this. This is 1. Because sine x over x is getting really, really close, as close as we want it to 1, as x gets close to 0. Whoa. Sine of pi over x. That's kind of a rough scientific notebook generated graph. It looks equally rough when we see what's going on with GeoGebra. Sine of pi over x. Let's see, I actually have to scoot this over a little bit. And don't want the object to be fixed, I want to remove it. Ah, there we go. Because when I do this pi over x, I have to be able to insert a pi. Pi over x. See what's going on there. As x gets close to 0, what is going on there?
The wavelength is getting shorter and shorter.
Yeah.
Well, it's larger.
Let me see if I can adjust the viewing window a little bit. I think maybe this, and then zoom in on it. Let me move out this way. Well, one more time. Let me move out this way a little bit. Okay, so when x equals 1, pi over 1 is pi, and the sine of pi is 0. So I think that makes sense that it should have a value there. What's this right here? 0.5. Pi divided by 0.5 is 2 pi, isn't it?
Mm-hmm.
That's 2 pi. We know the sine of 2 pi is equal to 1. Sorry, is equal to what? 0? Yes. What do we have here? That's supposed to be about, if it would let me enter it directly, 1/3 there. So pi divided by 1/3 is 3 pi. So sine of 3 pi is equal to 0. And evidently this is about 1/4. See the 0.25 there?
Yeah,
Close enough. So pi over 1/4 is 4 pi, so the sine of 4 pi. So if we look at x-intercepts of this graph, I think they're kind of interesting. 1, 1/2, 1/3, 1/4, would you believe 1/5, 1/6, 1/7, 1/8, 1/9, 1/10? How many x-intercepts does this thing have between there and 0? Yep. So as we look to see what's happening there, in between there and where it's headed, x equals 0, it's going to oscillate up and down and up and down and up and down infinitely often. And it's just...
It's like I can just keep making a decimal smaller by adding more number places.
So we get... So as x approaches 0, f of x is getting close to what number? Well, it's 1, it's -1, and it's 1, it's -1, 0. In fact, it takes on every value between -1 and 1 infinitely often in any open interval to the right, I guess any open interval including 0, I guess I should say. So what we're going to say is this limit does not exist. And sometimes there's a nice way to describe the manner in which a limit fails to exist. This one we could say it's due to oscillation, but there are other ways that we'll say that a limit fails to exist. So in our case, capture this picture. So we don't put an equal sign, we just say D-N-E, for does not exist. Because if it exists, it has to equal a number, a real number, maybe 0, maybe 1, maybe 5, maybe -1/2. And what we have to be able to do is go to that number, say if it were 1, and say, all right, we're going to say between there and there is where we want to be. As long as long as we're no farther away from 0, we've got a guarantee that it's going to stay in there. But it won't. No matter how close we insist that we be to 0, x be to 0, it's gonna be less than that infinitely often in that interval. So no, it does not exist. Okay, so that's kind of the feel for what we mean when we're talking about the limit. Now we move on to a more formal definition of limit using little Greek letter delta and little Greek letter epsilon, lowercase in each case. And let's see if this kind of corresponds to our intuition with regard to limits. I think the picture is very helpful. It is for me anyway. I'm kind of on the visual side. We're interested in what's happening close to C. X approaches C. So we've got the statement, the limit of f of x as x approaches C equals L. And we're trying to decide exactly what that means. How do we quantify that? And if there's some debate on the matter of whether or not a limit exists or whether or not it equals a particular number, how could we sell it in such a way that everybody in the room could agree, yeah, it exists, then it equals 5. End of argument. Well, suppose we're thinking that it equals L. Limit of f of x as x approaches C equals L. Then we're probably thinking that either there's a point on the graph of the function right here, or at least an open circle that the graph is getting close to, right there at the point CL. Let's look at the intuition here. Now we'll look at the formal definition. For each number epsilon greater than 0, for each number epsilon greater than 0, the epsilons are going to be associated with the function values, the y values. So on the graph, I'm going to draw a little parenthesis there and a parenthesis there. And I'm going to say this is L plus epsilon, and this is L minus epsilon. So we're wanting to say that the function actually does approach the value of L. So eventually, and by eventually I mean when we get close enough to C, eventually it's got to be between L plus epsilon and L minus epsilon. If it stays way high above L plus epsilon or way low, far away from L, then it's not getting close to L. If it's getting close to L, eventually it's going to be between L minus epsilon and L plus epsilon. It's got to happen. So let's draw a couple of horizontal lines here. That's where L plus epsilon is. And that's where L minus epsilon is. I don't have a function in mind. I suppose I could draw one, maybe one that's a little bit steeper than the one I drew earlier. So how about something that does something like that? Okay. It kind of looks like, because the graph goes through that point, it kind of looks like as x gets close to C, f of x does get close to L. So for each epsilon greater than 0, there exists a number delta greater than 0. Well, how do I find the delta? Well, I want to make sure that the graph stays in between the horizontal lines. So I don't want to go far to the left over here. If I consider values out here, it's not in between the horizontal lines. It's below the horizontal line. If I consider values over here and look at points on the graph up there, it's not in between the horizontal lines. It's above the horizontal line, L plus epsilon. Y equals L plus epsilon. So I've got to choose the x values close enough to C so that I ensure that the graph stays in between the horizontal lines whenever I'm within delta units of C. So I would think maybe in there somewhere. Does that look good? Something like that. And although I could go as far to the right as here, since it's going to be C minus delta to the left, and c plus delta to the right, I kind of have to pick the smaller of those two. It's not c minus a little bit, c plus a different little bit. We're going to do the same little bit on both sides. So we pick the smaller of the two to make sure that if we're in there, it's going to stay between the horizontal lines. So I'm going to say right there, that's going to be c minus delta, and mirror that on the other side. C plus delta is going to be right there. C plus delta. So for that particular choice of epsilon, this delta looks like it, ready for the air quotes, it works. It works. It does what we need it to do. That is, whenever the distance between this x minus c, absolute value of x minus c, it's if we pick an x in here, pick an x in there, and we take x minus c and take the absolute value of that, that difference is going to be less than delta, as long as it's in there. So whenever absolute value of x minus c is less than delta, then the absolute value of f of x minus L, well, where's f of x going to be? F of x, in this case, is right there, and right there. So that's f of x. So if we take the absolute value of f of x minus L, that's going to be less than epsilon. Okay? So, so yeah, I think if we pick any x that's no farther than delta away from c, then f of that x is going to be no farther than epsilon away from L. So that kind of quantifies it. If for any epsilon that you can give me, I can find a delta that works, that makes this happen, then we say the limit exists and equals out. Let's try this one. Don't say. All right, I think this may be the next example. Yeah, let f of x equals 2x, let f of x equal 2x minus 6, and observe that the limit of 2x minus 6 as x approaches 5 equals 4. What we'll see in the not too distant future is if we have a nice function. Polynomials are nice functions. And by nice, I pretty much mean continuous, but we haven't officially defined continuous yet, so I'm just going to say it's nice. Well behaved, no discontinuities. We haven't defined those either. If we have a function such as this, we can evaluate limits by substitution. If we take 5 and substitute it for x, 2 times 5 is 10, 10 minus 6 is 4. So if x is really, really close to 5, then 2 times x minus 6 is going to be really, really close to 4. That's basically what we're saying here. So that is the value of the limit. Let's look at the picture first, and then I'll come back and fill in these blanks, and you can kind of write along with me because I know you haven't had a chance to print this out and have a printed copy of it. So here's our function, f of x equals 2x minus 6. Might be good to zoom in on this just a little bit. Make sure that's not, no, I don't think it's going anywhere. Hope not anyway. Should have brought a mouse. Yeah, that's good. Does it specify the epsilon? No, we get to pick the epsilon. What would be a good value of epsilon here? Want to say 2? Mm-hmm. Let's say 2, since it's already there for us. So epsilon equals 2. So basically, there's 4, and there's 4 plus 2 right there, 4 minus 2 right there. If we change the value of epsilon, the rectangle gets, what happens to the rectangle? Gets taller or not so tall. We change the value of epsilon. But the value of epsilon, somebody's going to hand it to us, and they've handed it to us. 2, there it is. Now, how small does delta have to be to ensure that as long as we're no more than delta units away from 5, f of x is going to be no more than 2 units away from 4? It looks like if we stray as far as 1.5 units from 5, then f of x could be as much as 3 units away from 4, and that's too much. Not allowed to be more than 2 units away. So what delta should be maybe 1. That doesn't put us inside there, but if I say that x is less than 1 unit away from 5, maybe it's 5.9, maybe it's 4.1 or 2. Oops. No, that's what I wanted to say, 4.1 or 2. But it's less than 1 unit away from 5. Is it believable that f of x is going to be less than 2 units away from 4? Huh? So pick an x anywhere in between there. If we evaluate the function, then f of x is going to be somewhere in there. Now, if any delta works, a smaller delta will also work. Because I say, okay, suppose x is less than 0.7 units away from 5. Well, f of x is going to fall in between about right there and right there. So easily it falls between 2 and 6. So if delta equals 1 works, or epsilon equals 2, any smaller value of delta will also work. Now I've got to fill in the blanks. So here goes. How would we have discovered such a thing without the picture? Well, let epsilon equal 2, just like that. How close we would like it to be within 2 units of 4, between 6 and 2 basically. So we got to find a delta that works. So what I do is this. I know that absolute value of f of x minus 4, that is 2x minus 6 minus 4, has to be less than 2. Ultimately, we want that distance, f of x, to be no more than 2 units, or actually strictly less than 2 units away from 4. So what is... What?
Sorry, it seems like you could find this just using the slope.
You can. It's the reciprocal of the... Is the reciprocal the slope? Is it the reciprocal of the slope?
Sounds right.
What if we go with put a not a 3 there, but how about a 4? It should have followed it. Oh, that's disappointing. How primitive. See, my point A, instead of the 0.54, that's lame. I should have made it the point. I should have done this. I should have said A.
The asterisk would work. That seems to be about the right command. That way, if you want to change it, it would show that too.
Point A, f of A, if I truly have called it f, and I haven't called it f. I'm sorry. Have I called it f? F. Oh, it's 5. So I need the value of A. So A equals A equals I have more.
Would it be F5?
It would be,
F4.
but it's not gonna behave as I want it to. So I mean, we could adjust this, but
Scrap
it didn't do. Yeah, I'm gonna scrap it. It did do what I wanted to do because it's an older, less knowledgeable GeoGebra worksheet. So we'll move on. But you're right, there it is. For linear functions, the reciprocal is going to work for you. The reciprocal of the slope. Find a number delta such that this will work. Well, simplify. Absolute value of 2x minus 10 is less than 2. That's what we need eventually. We need to be able to say that. And we can simplify this a little bit. We can say, we can factor out the 2 like this. Because what we can control is this. We can control how close x is to 5. So we can control the absolute value of x minus 5, and we're working toward that. Let's see. Have to be a little careful. I can yank the 2 out only because the 2 is positive. Officially, properties of absolute value, the absolute value of the product is equal to the product of the absolute values, and it just happens that the absolute value of 2 is 2. So 2 times the absolute value of x minus 5 is less than 2. I want to be able to say something about the absolute value of x minus 5, so let's divide both sides by 2. When we do, we get the absolute value of x minus 5 is less than 1. So it would seem that if we can reverse all those arrows, then as long as the absolute value of x minus 5 is less than 1, then the absolute value of 2x minus 10 ought to be less than 2. So the absolute value of 2x minus 6 minus 4 ought to be less than 2. So this is finding it, and the B part is showing that it works. So in the B part, epsilon equals 2. We would just want to show that as long as delta equals 1, it's going to work. So suppose this is true, then what can we say? The absolute value of f of x minus 4 is equal to the absolute value of 2x minus 6 minus 4. This is going to seem like deja vu, by the way. It's going to say, didn't we just do that? I know you're going to be thinking that, and you'll have every right to think that. But we just did that to find the delta. Now we're doing again actually to show that the delta works. So, so this is what we have, and this is the absolute value of 2x minus 10. I'm going to skip this step right here and just say this is 2 times the absolute value of x minus 5. And so this is, well, if we know that the absolute value of x minus 5 is less than 1, and we're assuming that right here. We're supposing the absolute value of x minus 5 is less than 1. Would it make sense then to say that 2 times the absolute, that 2 times the absolute value of x minus 5 is less than 2? Could you multiply both sides by 2? Sure. So this is, no. 2 times 1, I guess. The fact that it's 1 is, so this is less than 2.
So where did 2x minus 10 come from?
The 2x minus 10, just the minus 6 minus 4. Just kind of simplifying that expression. So that shows it for that particular epsilon. Occasionally I'll have a GeoGebra worksheet and upload it to GeoGebra Tube so that you can play around with it yourself. And it would fit on the screen if I hadn't changed my aspect ratio. Or my resolution, I guess I should say.
It'll really fit better with the wider aspect ratio as well.
This will probably be okay. So what it does is it gives us a function, and it says, it looks like the limit of f of x, it doesn't tell us what the function is, that will remain a mystery. It involves a logarithm in this case. But the limit of f of x as x approaches 3 equals 5. Let epsilon equal 1. What value of delta looks like it's going to work here? Well, it would be okay for delta equal 1 over on the right-hand side because we're already inside the rectangle. But if x is too far to the left, say, let's see, from here to there is about, what, 0.7, 0.8, then the function values are well away from 3. We wanted it to be, sorry, from 5. we want to be close to 5 because that's our L. So I'm going to slide the slider until we get a delta that works. There we go. So, as long as we're no more than 0.63 units away from 3, then f of x is going to be no more than 1 unit away from, or actually less than 1 unit away from 5. So it'll recompute and give me another one. Maybe I didn't click it properly. There we go. Linear one. Okay, we just did this. So epsilon equals 1.6. Unfortunately, the slope of this is 3, I think. Slope is 3. So we'd want to take the 1.6 and divide it by 3, I think. What's 1.6 divided by 3? 0.53 repeating. So when we get to 0.53, that ought to be small enough. Yep, there we go. 0.51 works, 0.52 works, 0.53 works, 0.54 does not work. But 0.53 is a small enough delta. So as long as x is within 0.53 or less than 0.53 units away from 4, then f of x is going to be less than 1.6 units away from 8. One more. Oh, some curvature to it. This polynomial with an x cubed term in it, I forget exactly what it was. It looks like the limit of f of x as x approaches 4 is 7. It's a continuous function. F of 4 actually is 7 there. But also the limit exists there. So what? Epsilon equals 1.3. And you can see the 1.3, right? You look at this and you see from there to there, that's 1.3 units. And from there down to there, that's 1.3 units. How close are we going to have to be to 4 in order to be inside the box? No more than 1.3 or less than 1.3 units away from 7.
I just got a third.
Does it look like a third? We're good there, but we got to be good there too. 0.26. Is that good? Well, it says it is. So as long as we're less than 0.26 units away from 4, then we're going to be, the function is going to be less than 1.3 units away from 7. So play around with that GeoGebra worksheet if you'd like to. Oops. Let's try it with an arbitrary epsilon. Arbitrary epsilon. Process looks very much the same, except I really don't have a nice picture to give you. Let f of x equal 4x minus 1. I want to use the epsilon delta definition. Plug this in. To prove it, limit of f of x as x approaches 3 equals 11. First of all, you think it might be true. X gets really close to 3. Is 4 times x minus 1 going to be really close to 11? Well, since 4 times 3 minus 1 actually equals 11, yeah, you figure it's going to be pretty close. This is a well-behaved function. So what we need eventually is this. We need, as our final punchline at the end, to be able to say, aha, absolute value of f of x minus 11, sure enough, is less than epsilon. When we conclude that, we'll be done. So that means that the absolute value of 4x minus 1 minus 11 will have been shown to be less than epsilon. Okay, let's work on that expression. See, we've got control, since x is approaching 5, we've got control over the absolute value of x minus 3. If we can express this in terms of the absolute value of x minus 3, then we'll have something that we can kind of work with. So we'll keep working on it. Simplify absolute value of 4x minus 12. We need that to be less than epsilon, but I think we can get there. Because 4 is positive, when we factor out the 4, we can bring the 4 out of the absolute value bars and write 4 times the absolute value of x minus 3 is less than epsilon. So if we can get there, I think we can find our way to the end. So if we need that expression to be less than epsilon, what kind of requirement should we then place on this expression? It needs to be less than what? Epsilon divided by 4, yeah. This needs to be less than epsilon divided by 4, so that's our delta. That's our delta. Delta equals epsilon over 4. This can be considered just kind of scratch work. This is really not part of the proof, but it's finding a delta that works. That's going to work for an arbitrary epsilon. So we want to show that the delta that we found actually works. So imagine someone hands us an arbitrary epsilon greater than 0. They're not going to tell us what it is. They're just going to give us epsilon greater than 0. And let delta equal epsilon over 4. Let delta equal epsilon over 4. And suppose that x is actually within delta units of 3. Absolute value of x minus 3 is less than delta. How to show this? Well, I like to start with the expression, the absolute value of f of x minus 11. And if I can write an equal sign, an equal sign, an equal sign, eventually a less than symbol, and conclude with an epsilon at the end, then we can string them all together, and we can conclude that the absolute value of f of x minus 11 is less than epsilon. So here goes. This equals the absolute value of, 4x minus 1 minus 11. And if I had more space, I would work my way down the page. In fact, I don't feel really all that good about this, so I'm going to put it up there. This equals the absolute value of 4x minus 12. This equals 4 times the absolute value of x minus 3. I know, been there, done that. But we did all that, so this would work. Now, here's the key step. And I think this is probably the most challenging step in the process. We come back here and look and see what we're supposing. We're supposing that the absolute value of x minus 3 is less than delta. Well, if we're supposing that, then 4 times the absolute value of x minus 3 is less than what? 4 delta. So this is less than 4 delta. But what's delta? Epsilon over 4. So this equals 4 times epsilon over 4, which equals epsilon. So this expression is equal to this, which is equal to this, which is equal to this, which is less than this, which is equal to this, which equals epsilon. So string them all together, and the absolute value of f of x minus 11 is less than epsilon. So that concludes it. And that's probably a good place to conclude the first day of class.